Hello everyone, Happy New Year and welcome to Ignited Soul. This is the very first video in this year, and now I'm not representing myself, I'm representing Ignited Soul. This is established in the year 2020 and the first batch of Ignited Soul will resume its class from the 1st of February, and I will be a part of Ignited Soul, taking care of physics and mathematics. Apart from me, there will be other faculty who will be taking care of chemistry, organic, inorganic, physical, and biology. Most of our faculties are from IITs. So they are IIT graduates or PhDs from IITs or central universities like Calcutta University. And most of them are professional in their field, like some of them are teaching for an academy, some of them are teaching for other premier coaching institute, and they will be joining us for chemistry and biology. So, regarding today's class, or rather the first class for this year, today I'm going to teach about the very basic concept relating to numbers. And to teach today's topic, I am referring to the book Elements of Algebra. This is the book I am referring to, Elements of Algebra, written by none other than Leonard Euler, and it has got additional notes from Bernoulli and Lagrange, and I'm using the 1828 printed version because nowadays we don't get this book anymore. And if you want to prepare yourself for IIT or Mathematics Olympiad, then this is the very basic book that you need to study. So I'm using this book as reference, and then apart from using this book as reference, I use course notes from Stanford Universities while preparing these class notes. So in today's class, we'll be looking into numbers, how basically as a wannabe mathematician, let's say, or if you want to do well or represent India in Olympiad, or if you want to be a professional mathematician in future, so how basically you need to think about numbers. Can we visualize number? We will try to see the very basic concept regarding numbers, as I mentioned. Then we'll be looking into positive and negative number. How can you visualize positive and negative number? How can you identify and think about positive and negative number? Then we'll be looking into prime number. What is composite number? And then we'll be looking into the fundamental theorem of arithmetic. We'll be looking into the fact that while prime numbers are unique, and then we'll further look into why prime numbers are infinite. We'll try to figure out why positive into positive is positive, why negative into negative is positive, why positive into negative is negative. We'll try to figure out a prime number, if there is some way by which we can figure out if any given number is a prime or not. And then we'll try to see if it is ever possible to generate an equation, or to frame an equation rather, to generate prime number. If we can frame some equation from which we can get all the different types of prime numbers, if ever such sort of equation is possible or not, and if it is not possible, why is it not possible? So we'll try to look into that, and then we'll end the discussion with why 0 is an even number and why 1 is not a prime number. We'll try to look into the logical argument, and the last but not the least, we'll try to have an intuitive look into prime number theorem. Let's say if someone asks you, can you guess the number of prime numbers you can get less than 1 billion? How many prime numbers are possibly there less than a billion? If the number is 1 billion, how many prime numbers possibly are there? So we'll try to find a way to look into this. But we won't go into the mathematical detail and rigorous in this particular case. Rather, we'll try to look into the equation from intuitive point of view. So let's try to look into numbers. Whenever we look into numbers, what basically you need to think of? Let's say if someone asks you 1, can you visualize 1? One way to visualize 1 is you just write the number 1. But this is just a symbol. So visualizing 1 as this does not make any sense, because this is just some symbol, some abstract symbol probably, or is it? Or is it another way of probably I have got something and this distance is 1, I can call this to be 1. But again, if I assume this thing to be 1, let's say I am assuming this to be 1, you might assume this whole thing to be 1. So 1 might not be standard. For me, I might consider this to be standard as 1, and for you, you can even consider this to be 1. So we require some sort of uniformity whenever we say number 1. If I'm specifying in terms of length, so probably this could be 1, even this could be 1, but then we need some sort of uniformity. So basically, this whole idea of looking at number in this form probably is not a very correct way of looking at numbers. Probably the best way to visualize or think about number 1 is, now if you try to look into this, it is my consideration and it is your consideration for 1. What essentially is common in this one and this one is, this has got a starting point and this has got an end point. This has got a starting point and this has got an end point. So any line joining two endpoints, I can call that to be 1. Now depending on the distance, either I can call it centimeter or in terms of meter. So the unit could be different, and because the unit could be different, so the length could be different. Basically, what is the exact way of representing a number probably is, it is the distance between 2 points. And that is 1. Now if this is 1, I can get one more point, add up this 2, and then this becomes 2. Similarly, this becomes 3 now. So this way I can keep on repeating it and we can generate more numbers. Now if this is the case that we are considering the distance between 2 points to be 1, and because I have got 2 points, so always I can bisect it, and then if this I consider as 1, so then this becomes half. Again I have got these 2 points now, the new 2 points, and again I can bisect it, and now this can become the new number 1. Again I can bisect it, and so if I consider this to be 1, so now this is half, this is 1/4, this is 1/8, and this way we can get fractions as well. So I can get infinite number of fractions and I can get infinite numbers just by for infinite numbers. One point, add up, another point, add up, another point, add up. So this way I can generate infinite numbers from one number, and then if I got 2 points, I can bisect, again keep on bisecting, again bisecting, and this way I can generate infinite fractions as well. So basically this is the way by which you need to think about numbers. Now, how you need to visualize positive and negative number, and zero for that matter. Let's say I owe, or rather, let's say I got $10 with me. So you can say, well, this is positive. I got positive because I got something. There could be 3 cases. First is I got $10. Next is you might, or rather I might not be having anything. In that case it will be 0. And the third is you might be, or rather I might require to give you $10. So in that case I got negative. So basically how you need to think about positive, negative and 0, you need to think in terms of whether you got something or whether you are required to pay something to someone. So if you are required to pay something to someone, in that case that would be negative. If you are having something, in that case that is positive, and if you got nothing, in that case that is 0. So basically you need to think about a positive, negative and 0 in terms of whether you got, whether you need to pay, or whether you got nothing. Next is how you need to think about addition, subtraction, multiplication and division. You can think about addition as sliding of 2 rulers. You can have one ruler with some points being marked on it, and you can have other ruler with the points being marked on it. And addition, you can think in terms of sliding of 2 rulers. So initially 0 and 0 of both are matching against each other. Now let's say if I need to move by 3 units, so move by 3 units, so that is plus 3. Move in the other direction, it becomes minus 3. So you can think about addition and subtraction as moving of 2 rulers against each other as a sliding action. Next is how can we visualize multiplication. We can think about multiplication in terms of stretching action. Let's say I've got 3 and you need to multiply 3 with 3. So we know 3 times 3 is 9. So you can think of this as we have got a 3 marked in a rubber band, and this particular rubber band you can stretch it by 9 times, and this way you can get 9. So multiplication can be thought as some sort of a stretching action where the ruler is a flexible ruler that can be stretched, and that's how you need to think about multiplication. What about division? Division you can think in terms of squeezing action. Let's say you have got something like 2, you squeeze it and then it becomes half. You squeeze it further half. So initially 2, squeeze it, it becomes 1, squeeze further, half, squeeze further, 1/4. So division basically is a squeezing action. Multiplication is stretching action. Why you need to think multiplication, addition, subtraction, division in terms of sliding and stretching and squeezing is because this will be very helpful whenever you will be doing calculus. So we'll be looking into that, how these are going to be helpful. Another way of looking into multiplication. Let's say you are being given multiply x into y. How you need to visualize it. One way I told is stretching, and the other way is probably you got something as x and then we have got something as y, so this becomes xy. So you can think of xy in terms of some figure. So xy probably is a rectangle where x could be its width and y could be the length or whatever it is. So you can think about multiplication as a figure in certain cases. Now it depends on the type of question that you are required to the answer, what type of idea you need to have in mind, but you need to have a very open mind that how you can think about multiplication. One is by stretching action and the other is in terms of figure. Now whenever we are writing something in terms of figure, that means we are also writing in terms of dimension. So that means this gives us an idea about dimension. So x into y, as you can see, is a two-dimension figure. So these are some of the very basic things that you need to keep in mind. So what is a number? First of all, whenever you need to visualize number, you need to think any number or a number one is, I've got one point, I've got another point, and I've got some line in between them, and that could be 1. And I can take one more point, and this way I can generate infinite number of points and keep on adding individual points, and this way I can end up getting infinite numbers. And similarly, I've got two numbers, I can bisect it, get half, bisect it further half, and this way I can generate infinite number of fractions. How you need to think about addition? We need to think about addition in terms of sliding action. How you need to think about subtraction, again by sliding action. How can you think about multiplication in terms of stretching? How you need to think about division in terms of squeezing? How you need to visualize multiplication in diagram form. So you need to think multiplication as some sort of planar figure. If it is xy, so it is a two-dimension figure. If it is x cube, in that case definitely it's a three-dimension figure. So it gives you an idea about how numbers even can have dimensions. So it depends on the type of question, what way you need to think and visualize numbers. Next is, we'll be trying to look into well-ordered axiom. So what exactly is well-ordered axiom? So any set, we consider a set, any set, and if we just plug in some numbers, will have one of the elements which will be the least element. And because this number is the least element, so we can generate additional number just by adding 1 to 8, because we know we can always generate number by adding 1 to 8. So if you got a set, and if that particular set has got the least number, so we can always generate the next and next and next element just by adding one number to 8. And this way we can get a complete set of numbers which will be included in that particular set. Now, why this is essential? Whenever, let's say if you are asked to prove that the set of natural number exists, how you are required to prove? Well, maybe this is the set N, which represent the set of natural numbers starting from 1, 2, 3, 4, all the way to N. Now, for me to prove that this particular number exists, what I can do is probably I can assume that, well, I might be having one more set, and this set consists of the least element present in N. And then one more set probably which will have none of the elements which are present in A. So here I've got 1, 2, 3 all the way up to N, and the next set A, as I mentioned, that it has the smallest element 1. Because it has got the smallest element, so I can always generate the next one by adding one more to it, and this way I can get 2. Similarly, I can get 3, 4 all the way to N. Now A dash, as I mentioned, will be the set of those elements which are not present in A. So because in case of A dash, 1 is missing, so quite natural 2 will also be missing. And similarly 3 is missing, 4 is missing, all the way till n, and each one of them are missing. So that implies that A dash is an empty set. That means all the elements of n are present in A. And this way we are duplicating each element of natural number into another set. And if this is complete, this is also complete. So in order to prove existence of certain things, we can adopt this particular way of proving things. Next, we'll try to see why positive into positive is positive, why positive into negative is negative, and why negative into negative is positive. We'll try to see from two different points of view, one by visualizing and another by logical argument. This logical argument again given by Euler. So what Euler gave, and again these arguments are mentioned in this book, Elements of Algebra, the logical argument part. So the logical argument part as well as the visualization part. So let's say this is A and this is B. So A into B is this one, and quite natural this is positive. So positive A into positive B is this AB, which itself is positive. Now assume A and this one is C and this one is B minus C. I am considering the entire length to be B. So now if I am required to find what is A into B minus C. So A into B minus C is this one. Correct? So A into B minus C is equal to this whole thing, which is AB minus this portion. What is this portion? This complete portion was B. This is B minus C. So this is C minus, and this one is A. So I've got C here and I've got A here. So minus this portion, minus AC. So positive into negative is negative, as you can see here. So this is using visualization. Next is why negative into negative is positive. Again, we will try to see that this is A, this is B. Probably I'm dividing it like this, and this assume is C and this is D. So from here to here it is B minus D, and from here to here it is A minus C. So what is A minus C into B minus D? If I am required to find this, so A minus C into B minus D is this portion, which is this whole portion, which is A into B, minus this portion, which is C. So AB is the complete one, minus this triangle, which is C into B, minus this, which is this complete is A, and this portion, so this is A and this is D, AB, But then whenever I am subtracting this and I am subtracting this, I am subtracting this particular box 2 times. Because I am subtracting this particular box 2 times, so I need to add it up. Why negative into negative is positive? This is because of the fact that if I am required to calculate the area of this one, so that equals area of this complete thing minus area of this thing minus area of this thing, and because we are subtracting each of this area, so we are actually subtracting this 2 times, so we need to add it up. And what is this? C into D. So C into D is added up, and what is C into D is negative into negative, and because these are added up together, so it becomes C into D. Next, we'll try to see why or how rather the numbers are made up of. I'm claiming that numbers are made up of prime. All numbers are made up of prime numbers. And that is why the study of prime is the core of mathematics. You cannot study mathematics properly until and unless you know how prime numbers, what are the patterns of prime number, how prime numbers are related to abnormal numbers, how numbers are framed using prime numbers. So a lot of theories, a whole lot of theories are there involving prime numbers. Or you might say that our complete mathematics is based on prime number. So we'll try to focus our next discussion on prime number. So as I mentioned, that all numbers are made up of or you can generate numbers just by adding 1 to it. So this way we'll get whole lot of numbers starting from 1 to infinity. We will not look into numbers up to infinity. Maybe we'll get the first number here and then add one more number to generate or to get the next one more to get the next, one more to get the next, and this way I can generate number till some value. Now, so assume, let's say this value, I'm starting from 1 and probably 2, 3, 4, 5, 6, 7, 8. Now, if I can generate number till 8 from 1, so I must be able to undo the whole thing and get back to 1. So in order to get back to 1, what we can do, well, one of the thing is starting from 4, we wrap it up, and this way this whole thing becomes 4 into 2. One more thing we can do, we can further take 2 and then wrap it up like this and like this, so we'll have some sort of sandwich of 2. Now if I am required to further divide this number, I cannot do so except for the fact that I can only divide 1 and 1. So you take any number and then if you try to reverse the process, you can reverse it back and then after a certain point of time you cannot reverse it back or you cannot break it down into anything except 1. So those numbers will be the prime number. If you are not exactly getting what I'm trying to say is, let's say this is some number. So I am dividing it by half. Next I am again dividing it by half. Next again I am dividing it. So probably after this point of time I am not able to divide it further, because after this if I try to break it down it becomes 1. So now if that is the case, so then this is a prime number. So basically what I mean to say is all numbers whatever you can think of are all made up of primes. So numbers are made up of primes. And since numbers are infinite, so prime numbers must be infinite as well. What else we can say? So as I mentioned to you, all numbers are made up of prime, and it is made up of prime factors in a very unique way. And this is what we call as the fundamental theorem of arithmetic, so that any number are made up of primes or prime factors in a very specific way, or rather in a very unique way. And in order to prove it, let us assume that a number cannot be, we cannot break down a number into prime, possibly, or a number if it is, or we are assuming that the number is not made up of prime, instead a number can be made using composite as well. So we are assuming it, so we are trying to prove it that all numbers are made up of prime, and to prove it we are using contradiction. We are trying to prove that the numbers are actually made up of prime, but in order to prove it we are assuming that if it is possible ever for a number not to be made up of primes, and if it is not made up of prime, then it is made up of composite. So we are assuming that we have got a number n. Probably this is the first number n, which cannot be written in terms of prime factors, possibly. So it is made up of composite c, or rather it is made up of product of two composite numbers c1 and c2. So we are assuming that n is the very first number which you cannot break it down into prime factors if ever it is possible. And because it is not possible to break it down into prime numbers, and we are assuming that it is made up of composite numbers c1 and c2, where c1 and c2 definitely are less than n1, and n1 is the first number. Remember that I assume that it cannot be you cannot break it down into primes. So if that is the case, that n is equal to c1 into c2, where c1 and c2 are composite number, but we know this c1 itself is product of prime. This again is a product of prime. So the whole thing actually is a product of prime. So our assumption that this number is not a product of prime, and it is a product of composite, is wrong. So whatever we assumed actually is wrong. So any number are made up of prime numbers or prime factors. And next is, these prime factors are unique. What I meant to say by unique is, assume a number 8 again. So 8 is 2 into 2 into 2. Assume a number 6. 6 is 2 into 3, prime factors. Assume a number 5. 5 into 1, prime factors. Assume a number probably 12. 3 into 2 into 2. So what I mean by unique is, there is no other way by which you can represent 8 as a product of prime apart from this arrangement. There is no other way. This is the only way. Any number can be, well, you can break it down in terms of prime factors in only one specific way, and this is unique, and there is no other way by which you can break it down. Why is it so? So in order to prove it, we will be using, or rather we try to prove it. Assume that it is possible for any number n to be written as a product of prime in two different ways. So I assume this number n to be written first p1 into p2 into p3 into p4, and this way, probably up to pn. And again I assume, because I'm assuming that it is not possible, so again what we are doing is proving by contradiction. So again we are assuming that it is possible to write this number in terms of prime factors in two different ways. So again assume this n could be written in terms of another prime factors q1 into q2 into q3 all the way till qn. And here in this particular case, each of these prime number pi belongs to a prime number. Here as well, each of these qi belongs to prime number. Now I am assuming that it is possible to write any number as a product of prime in two different ways. So I am trying to prove by contradiction. So if it is possible, now if I try to divide this number by p1 and this number by p1 again, so that implies that this whole thing will be divided by p1, and this whole thing again is divided by P1. So if this whole thing is divided by P1, so I can cancel this P1 out. So what I am getting is from here to here. If ever it is possible again to write these prime numbers in terms of prime factors in different way, so as I am writing in terms of Q1 and all the way to Qn, and if I am able to divide it by P1, because the number in the left hand side is same, if I divide by n by P1 here and n by P1 here, so whatever the number in the left hand side are same. So if that is the case, the number in the right hand side should also be same. And if in this case it turns out to be, the result turns out to be P2 to Pn, so that means here also the P1 must cancel out Q1, or else this and this cannot be same. So if P1 cancel out Q1, it is only possible that Q1 is actually equal to P1. So my assumption that P1 and Q1 are different numbers and all numbers can be written as in terms of prime factors in different ways is totally absurd. So we arrive at a contradiction because it is not possible. So all numbers can be written in terms of prime factors in a very unique way. Next we will try to see why these prime numbers are infinite. Assume that, because we have seen that all numbers are made up of primes and they are written in terms of prime factors in a very unique way, assume that I have got the largest possible number n, and probably whatever prime number, I am assuming again that prime numbers are finite, and if prime numbers are finite, so whatever prime numbers are there, starting from P1 all the way till Pn, I am taking all or each of these prime numbers and multiplying each of these prime numbers, I am generating a number n. Now by well-ordered axiom we know that if I got a number n, I can generate the next number n and the next number just by adding 1 to it. Now if this has got the entire prime numbers in it, so quite natural, n plus 1 will have a prime number which will be different from each of these, and because I have assumed that these are the only set of prime numbers and I have used the entire set assuming this to be finite, so that means here, because I need to use additional prime number to designate or to look into n plus 1 or to prime factor n plus 1, so that implies that the prime numbers are not finite, rather it is infinite. So prime numbers are infinite because numbers are infinite. Numbers are unique, and that is why prime numbers are unique. So these are the very basic thing that you need to keep in mind. So what we have seen so far is, or rather are, prime numbers are infinite. Numbers are made up of prime, or all numbers are having prime factors, and these numbers are all unique, or rather prime factors are all unique, and prime numbers are infinite. So these are a few things that we have seen. So apart from this, what else we can see? Let's try to find out why or whether it is possible just by looking at the number, if we can say if any number is a prime number or not. I'm taking a number 91 for example, and another number 97 for example, and another number maybe 93 for example, and we'll try to see whether any of or each of these are prime or not, or any of these are prime or not. We'll try to see or look into that. Now we know, so these are just some numbers. So we can just designate any number by n. Now this n is also equal to root over of n into root over of n, correct? And this number n can also be written as a product of prime in a unique way. So this could be, or I can write down n in terms of product of prime P1 into P2. Now, because n I can write in terms of P1 into P2 product of prime, and n can also be written as square root of n into square root of n, and So now if I write root n into root n divided by p1 into p2. Now this root n in itself could be prime. There are two possibilities. Either it could be prime or it could be composite. If it is composite, it can be further, you can break it down in terms of product of prime, or it could be prime. Now, if that is the case, this must be divisible, because ultimately the whole thing, it is n divided by n actually, so it needs to be 1. That means the whole thing in the top and bottom need to be cancelled out. So this n, if it is written in terms of prime factors, so the p1 must cancel whatever the prime number prime factors we are getting in case of root n, if root n is composite number. So what I mean to say is, let's say root 93. In order for me to check whether whether 93 is prime or not, so I can write down 93 as equal to root of 93 into root of 93. And I know this can also be, you can break it down in terms of prime factors. In case of root 93, we know root over of 100 is 10. So root over of 93 will be somewhat lesser than 10. So we'll try to look into all the prime factors which are, or all the prime numbers which are lesser than 10. Because if that is the case, root of 93 should have been met using these prime numbers only. So root of 93, what could be the possible prime numbers less than 10? So it will be 2, 3, 5, 7. What else? That's it. So we'll try to see whether 93 is divisible by any of these 2, 3, 5, 7. Whether 93 is divisible by 5? No. Whether 93 is divisible by 3? Yes. So root of 93 is not a prime number. So this is not prime. So this one is not a prime number. What about 91? So 91 is equal to root over of 91 into root over of 91. So root over of 91 into root over of 91 divided by the possible prime numbers less than 100. Again, 2, 3, 5, 7. Whether any of this number are dividing 91. Definitely 2 is not dividing 91. Whether 3 is dividing 91. No. 5, no. 7, yes. So this is also not a prime number. What about 97? So if it is 97, then 97 is equal to root over of 97 into 97. So this is 97, this is 97, again 2, 3, 5, 7. So now we'll try to see whether 97 or 2 divides 97. Quite natural, 2 doesn't divide 97. Whether 3 divides 97? Well, yeah. Or no. 9 plus 7 is 16. So 16 definitely is not divisible by 3. So 97, 3 does not divide 97. 5 by natural does not divide 97. Now whether 7 is dividing 97? Well, 97 is 7, 1, 7, 8, 9, 27. And 27, definitely 7 is not dividing 27. So 97 is not divisible by 7. So 97 is neither divisible by 2, it is not divisible by 3, it is not divisible by 4, it is not divisible by 7. So that means this is a prime number. Next we'll try to see if at all it is possible for us to have some sort of a machine which can generate prime number, maybe some sort of a quadratic equation which can generate prime numbers. Assume that the first thing is, I'm telling you it is not possible to generate prime numbers, and I'm telling so it is not possible to generate prime number. In order to prove my statement, we are again using proof by contradiction. So I'm possibly considering the fact that it is possible to generate prime numbers by certain equation, and let the equation be px, and I'm assuming that this equation is some sort of a quadratic equation, probably in the form of ax squared minus bx plus c. I'm assuming that it is possible to generate prime numbers by some quadratic equation having a form like this. Now, because this number is generating prime numbers, so if the value of x turns out to be 0, so this implies the whole thing from here to here will be a into 0 squared minus b into 0 plus c. And because I am assuming that this is generating prime number and this whole thing is 0, that means this c is prime number. So that means c basically is prime number. So if this equation can ever generate prime number, in that case c definitely will be a prime number. So maybe I can rewrite this equation as p of x is equal to, probably I can take the x out here, and we can say, well, this is equal to ax minus b plus p, and now c is the transform p, because c is a prime number. As we have seen, if at all it is possible to generate an equation which generate prime number, in that case the c definitely needs to be a prime number. So, well, I can p of x is equal to, probably this is another equation or another function in the form of qx, probably, if you want, or maybe we can just keep it like it, and well, we'll just keep it this way. And now I am replacing the value of x with p1. So if that is the case, this whole thing will become p1 a, p1 minus b plus b, and this whole thing again will be a prime number, if it is possible. Similarly, p of twice of p1 is equal to 2p1 a into 2p1 minus b plus p. Now, if this whole number again is divided by p1, or if this number is divided by 2, if divided by p1 again, so this one turns out to be 1 and this one turns out to be 2. And similarly for p of 3p1, it turns out to be 3. Whereas in this case, because this is prime number, so if it is divisible, so because it is a prime number, so this number is only divisible by itself, and that means here in the right hand side we end up getting only 1, 1, 1 and always 1, whereas here we are getting 1, 2, 3, 4 and all the way till infinity. So that means in the left hand side we are having a number starting from 1 till infinity, whereas in the right hand side I am getting same 1, 1, 1, 1, 1, 1 pattern. So that means this equation is not practically possible. So my assumption that it is possible to generate a prime number is wrong. So generation of prime number is not possible. Next we will try to look into the prime number theorem. Now, looking into prime number theorem, as I said that this is very mathematically rigorous, so I won't be going into detail, but just some intuition that why this makes some sense. Let's say if someone asks you, tell us the number of prime number, all the prime numbers possible, how many prime numbers are there less than 1 billion. If someone asks you, can you or will you be able to answer? Probably we can answer, take each of this number and then see whether these numbers are prime or not. So this way it will take a whole lot of time. But if there is some easier way just to have some sort of a idea regarding the possible number of prime number or all the numbers less than 1 billion. Is there some way? Yes, definitely there is some way, and for that we have got the prime number theorem P and T. So we will be trying to look into P and T. So the next thing is prime number theorem. And as I mentioned, we won't be going into the mathematical detail because it is way beyond the scope of this whole discussion. So I won't be going into the detail of the prime number theorem, but just to have some intuition regarding why this formula will make some sense. If we write down all the numbers, let's say I'm writing the number 1 to 30, all the numbers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now if we try to figure out all the prime numbers between 1 to 10, so 2 is a prime number, we know 3 is a prime number, 5 is a prime number, 7 is a prime number. Between 11 to 20, well, 11 is a prime number, 13 is a prime number, 17 is a prime number, 19 is a prime number. Between 21 to 30, well, 23 is a prime number and 29 is a prime number. So how many prime numbers we get less than 10? So we have got 1, 2, 3, 4. So we have got 4 prime numbers less than 10. How many prime numbers we have got less than 20? So I have got 11, 13, additional 11, 13, 17 and 19. So we have got total 8 prime numbers between or numbers less than 20. How many prime number we are getting less than 30? So 8 plus another 2, 23, 29, which is 10. Again, if we further write it down, 31, 32, 33, 34, 35, 36, 37, 38, 39 and 40. So we know 31 is prime number, we know 37 is prime number. So 31, 37, another 2, which is 12. So what we can see is initially we started off with 4 less than 10, we have got 4 prime numbers, then 8, then next 10, then 12. So this way the prime number, the number of primes are increasing. But if you see the increasing pattern, it is not linear, but rather what we will find is the rate of increase in the prime number is not a linear pattern, rather it follows a logarithmic pattern. Initially it will be more and then gradually it will be lesser. So the curve will be, if we try to look at the number of prime numbers, so initially it will be more and then gradually it will decrease and finally will be straightening up. So the prime number value or the number of primes will be decreased, or the density of prime number will be getting lesser and lesser and lesser. So it is not following a linear pattern, rather it is following a logarithmic pattern. But the increase in the numbers, as you can see here, is linear. 1 to 10, it's a 10 points it is traveled, and 11 to 20, another 10 points it traveled, 21 to the 30, another 10 points it traveled. So the increase in the number is not linear. Sorry, increase in the number is linear, but the way the prime numbers are increased, it is logarithmic. So, but what we can see here is, if we try to see the increase in the prime number, so 4, 8, 10, so there is an increase, but the increase is not linear, it is logarithmic as I mentioned, and then the numbers are increasing at a linear rate. Because at the end of the day, what we have seen is that there is a net increase in the prime number. So if I need to figure out how many prime numbers are there between, or how many prime numbers are there less than n, so probably we can write, well, the number of prime number less than n is equal to, because the net effect is an increase. So if I put n here, and if I put log of n here, so log of n is increasing, but the rate of increase is not very high. It is increasing and then almost constant. It is increasing and almost, after that, after a certain point of time, it is almost constant. In case of n, it is increasing. So the net effect is an increase, because this is increasing and this is initially was increasing and then it is almost getting constant and constant. So here at the top we have got the intensity is increasing, and here initially the rate was higher and then gradually it levels out. So the net effect will be an increase. Now if I put log of n at the top and n at the bottom, because the intensity of n is high, whereas intensity of log n initially was high and then gradually it flattens out. So initially was very high and then gradually it flattens out. So that means the net effect is going to be lesser, because this is increasing and the whole thing, the density of prime number, as we have seen, is increasing, and at the bottom, if something is moving at a very higher rate, so quite natural the net effect, because this is having very high intensity, so because of this density will be decreased. But we have seen that the number of prime number actually is increasing, so we cannot have this value of n at the bottom, it needs to be at the top, whereas the value of log needs to be at the bottom. So the prime number, if someone asks you how many prime numbers are less than 1 billion, how many prime numbers will get less than a billion, or maybe less than 1000, so probably we'll try to say less than 1000. So number of prime number, number of primes which are less than 1000 is equal to 1000 divided by the natural log of 1000, and you take the calculator, plug in the value of natural log of 1000, whatever value you get, and 1000 you put, you divide, you will get some number, and that will be an approximation of the number of primes you will have less than 1000. Okay, so that is all about the prime number theorem. Again, this is not very mathematical rigorous, just some intuition that why this particular formula makes some sense. Now we'll try to see why 1 is not a prime number. Because as I mentioned that prime numbers can be written, or any number can be written in terms of prime products in a very unique way, and if ever it is possible for 1 to be a prime number, assume that 1 is a prime number. Now I'm writing prime factors of 3, so 3 is equal to 3 into 1. Now if I write this as 3 into 1 into 1, this also is correct. Now if I write 3 into 1 into 1 into 1, this also is correct, this also is correct, and each of these has a value of 3. So if 1 is a prime number, but in that case, because I can write this 3 into 1 in all different ways and still the value remains same, that means the actual definition of prime number, that the prime factors can, or any number can be written in terms of prime factors in a very unique way, is getting wrong here, because I can write these prime factors, if 1 is a prime factor, in different ways and still the value remains same. So 1 cannot be prime number. So 1 is never a prime number. And we'll end the discussion with collage conjecture. Again, it is not, it's a very nice problem, and it is it's a very famous problem. A lot of videos are there in the YouTube regarding collage conjecture, and again, a lot of videos are there. Everyone know the result. It is very easy to see why the thing holds, but till now no one actually knows why this makes sense, and it is not yet proved. So if anyone can prove collage conjecture, definitely his or her name will be there in the history, would be written in the mathematical history, and probably very huge cash money also you'll be getting as a reward, probably 1 million or so. So we'll try to see and do collage conjecture, because again it is related to numbers. So what collage conjecture says, you take any number. Let's say I'm taking a number 11. So it says that if a number is odd, in that case make it 3n plus 1. And if a number is even, then divide the number by 2. Very simple. So I'm taking a number 11, and we'll try to see what happens. If as I'm taking number 11, so 11 is odd number, so we'll follow 3n plus 1 rule. So 3 into 11 is 33 plus 1, 34. So if it is 11, it is getting converted into 34. Now 34 is even. Half of 34 is 34 divided by 2. 2 1 2, 14, 7. So this is 7. 7 is odd again. So now what we'll end up getting is 17 will be 17 into 3 plus 1. 3 into 7. So 3 into 17 is 3 7 is 21. This is 51 plus 1, which is 52. So this is 52. So 52 is again even. So divide by 2, which becomes 26. 26 is even again, divide by 2, it becomes 13. 13 is odd again. So again we'll follow 3n plus 1. So 3 into 39 plus 1. 3 into 39 is 3 9 are 7. 2, 3 3 is 9, 10, 11 plus 1. So 118, correct? So, 3 into not 39, sorry. So 13 is 3 into 13 plus 1, which is 39 plus 1, which is 40. So 40 divisible by, it's an odd number, sorry, even number, make it 20. Again, 20 is even, divide by 2 again, make it 10. 10 is again even, divide by 2, it becomes 5. 5 is odd, so 3 into 5 plus 1, 16. 16 is even, so divided by 2, it becomes half, 8. So 8 becomes 4, 4 becomes 2, and 2 becomes 1. So what I'm trying to say is, whatever number you take, all the number will end with 8, 4, 2, 1. This is known as collage conjecture. Any number you take, you just follow this pattern. If it is odd, make it 3n plus 1. If it is even, just divide by 2 and keep on iterating in this pattern. You will end up getting this 8, 4, 2, 1 sequence. So all numbers will end up with 8, 4, 2, 1 sequence. So why this happens, no one knows, and this is what collage conjecture is all about. So that's all for today, and we'll be looking into the next part, which will be about GCD, one of the most common topic, or probably the most important topic that is used, or a lot of questions are there in the mathematics Olympiad regarding GCD, a fundamental of GCD, and we'll try to look into GCD and all with a very mathematical approach, a very systematic approach. And okay, that's all for now. And make sure you like, comment, subscribe the video if you like it. And then Ignited Soul is open for registration. The classes will be starting from 1st of February. So in case you are interested in IIT, in case you are interested in going for Olympiad, make sure you come and visit us and get your enrollment done before definitely first. We have got total 60 seats available, and the classes or the classes will be or the entry rather is class 8 onwards, 9 onwards, 10 onwards, 11